Hi there, my name is Vlad Hrybok, and I am a Senior Partner Solutions Architect at AWS. Today we will look at how to leverage AWS App Mesh to control network traffic and to ensure consistent visibility of .NET Core applications. My own background is mostly in .NET development and architecture, so this video will showcase tools like Visual Studio, Visual Studio Code, and PowerShell, together with several tools originating in non-.NET or Windows technology stack. This video should be useful for non-Windows folks just as much because we will be running our sample applications in Linux containers and use cross-platform tools most of the time. Since we cover a fair amount of ground in this video, in case you're familiar with some of the material here, please take a look at this video description that has shortcut links to specific topics. For example, if you know how to build a container image and push it to AWS, then you may want to skip a few sections using the shortcut links in this video description. Since this video was prepared, the name of ALB Ingress Controller component was changed, and it is now known as AWS Load Balancer Controller. Please make a note of that as you follow this video. A major part of this video will be a live coding demo showing how typical DevOps challenges like building a canary deployment can be addressed using App Mesh network controls features, and how App Mesh's consistent visibility features make it possible to transform request tracing data captured by App Mesh into AWS X-Ray Service Map in a transparent and low-maintenance manner. That and quite a bit more is on today's menu. Let's check it out. Here are a few more details about what we will do today. I will give a brief introduction to the Service Mesh concept. We will review tools, components, and sample applications comprising the solution which we will build today. But as I mentioned, the main chunk of this video is a live coding demo where we'll do everything from scratch, starting with building an EKS cluster with Fargate. Then we'll install AWS Kubernetes integration components and create the mesh. We will package sample applications for installing them on EKS with App Mesh. Then we will install our sample application parts using canary rollout model. We will test the entire solution to ensure that the request chain works as designed. And finally, we will see the data about our services on the AWS X-Ray Service Map. After we are done with this demo, I will suggest practical hands-on exercises that should make App Mesh knowledge stick better and to make the knowledge more tangible. Let's go ahead and talk for a moment what AWS App Mesh is. Here is the App Mesh textbook definition. AWS App Mesh is a service mesh that makes it easy to monitor and control services. App Mesh standardizes how your services communicate, giving you end-to-end visibility and helping to ensure higher availability for your applications. App Mesh gives you consistent visibility and network traffic controls for every service in an application. I think I can hear some of you saying, what I got is that AWS App Mesh is a service mesh, but I'm not that familiar with a service mesh either. If we look up a service mesh definition, we find the following. A service mesh is the logical boundary for network traffic between the services that reside within it. Well, before I lose your attention with all these textbook definitions, let me try to give you a more practical description of a service mesh. Effectively, service meshes are like logical clusters where service discovery is easy. But unlike Kubernetes-specific service mesh, AWS App Mesh lets you build meshes that include Linux containers running on different container orchestrators, like Amazon Elastic Kubernetes Service, EKS, and Amazon Elastic Container Service, ECS, as well as on containers running on Amazon EC2 VMs. Service meshes in general, and AWS App Mesh in particular, let us see graphical representation of microservice relationships, see where errors originate, which are hard to trace otherwise, enable easy service discovery with simple service addresses that are not localized to physical clusters, give us easy-to-use tools for implementing blue-green and canary application version rollouts and rollbacks, plus quite a few more features that we won't have time to cover in one video. Regardless whether you are using AWS App Mesh or a commonly used open-source service mesh, you're likely to learn that the main part of either of them is an open source component called Envoy Proxy. So what's Envoy and what does it proxy? Envoy is technically a network traffic proxy, both regular proxy and reverse proxy, and for the Kubernetes case, it's living in so-called sidecar container. What this means in practice is that Envoy is an interceptor of inbound and outbound network traffic for your container. That's a proxy part, and it also means that Envoy-owned container is transparently injected into the Kubernetes pod where your application container runs. You may remember that Kubernetes pods may have multiple containers. Being a network traffic interceptor enables Envoy to do a lot of things that software developers often do in application code to instrument their business logic. Things like logging, performance monitoring, tracing, retrying on failures, sending error notifications, etc., commonly known in software development as cross-cutting concerns. Well-written software typically uses aspect-oriented programming frameworks to deal with cross-cutting concerns. While using aspect-oriented programming is a very good approach, Envoy takes this idea to the next level. It is like an aspect-oriented framework living outside of your application. Just like AOP frameworks, it intercepts your service calls and uses content of intercepted requests and responses to let you deal with cross-cutting concerns by using Envoy configuration settings rather than writing application code. Which takes us to the next point here. Most App Mesh resources names have virtual prefix, virtual nodes, virtual services, virtual routers, and so on. All those virtual resources don't really exist. Instead, virtual things get transformed into Envoy proxy configuration settings, which get sent to relevant Envoy proxies on the need-to-know basis. As an example, an in-mesh client application calling a service via an App Mesh virtual service and a virtual router will get its sidekick Envoy configured by the App Mesh to receive configuration settings matching data about the virtual service and virtual router, and then client applications Envoy will do all the necessary work of finding and calling actual service container. This way, all virtual mesh resources get transformed into tangible configuration settings and rules sent down to appropriate Envoy proxies, which then do all the actual work of routing, listening, calling, outputting telemetry data, and so on, just as an aspect-oriented framework interceptors in your application might have done it to complete similar tasks. As you can see, all those virtual resources is just a convenient abstraction to configure Envoy proxies without having to write configuration manually for each and every one of Envoys in the mesh. Before we dive into the demo, let me start with giving you a little bit of the context. The sample solution that we'll use today comprises two ASP.NET Core MVC applications. A REST service shown on the right returns the color name as a string. And on the left side of the screen is a screenshot of the client web UI application that calls the service and shows the color when the link on the page is clicked. Both applications have configuration settings defined in their respective appsettings.json files. For the service, the color to return is configurable, and for the client, the address of the service to call is configurable. In a few minutes during the live demo, we will build and run these applications. Here is a list of what we will need to complete our work today. An AWS account, Visual Studio 2019, Community Edition will be sufficient for our goals today. Visual Studio Code, which is optional but is really handy, especially with its excellent Docker and Kubernetes extensions. We will also employ following command line tools. Git, so we could use several open source scripts and templates, AWS, the command line interface for managing AWS resources, kubectl, the CLI for managing Kubernetes resources, EKS-ctl, a really handy convenience utility for working with Amazon EKS, Helm, the package manager for Kubernetes, letting us create Kubernetes installers for our applications, PowerShell 7 and AWS tools for PowerShell for cross-platform scripting of AWS resources. Regarding skills that will be important to have today, here is a quick refresher of a few fundamentals. Container is a way of packaging your application binaries in such a way that it includes all application dependencies down to the operating system, and then running your app in a highly isolated sandbox manner in a very consistent runtime environment. You may think of a container as a binary package that behaves in exactly the same way regardless where it runs on your development laptop or at scale on a cloud. Container's killer use case is to eliminate works on my box problem. Well, if a container is like an exe that never falls victim to the DLL hell problem, Kubernetes is more like a cluster of IaaS servers. It's a compute service for running containers at scale, meaning it will schedule containers to run on cluster node computers or VMs, it will restart containers as they crash, and it will maintain stable network addresses for containers that go in and out of existence. Kubernetes' defining trait is a declarative nature of its infrastructure as code manifest files that describe desired final state of resources running on a cluster. Helm is a package manager for Kubernetes, or you may think of it as a tool for creating and running application installers for Kubernetes, sort of like MSI installer for Windows applications. One thing that may not be self-evident is that AWS App Mesh is compatible with Linux containers only, and not with Windows containers. The reason is that Envoy Proxy is for Linux only and therefore cannot be injected into Windows Kubernetes pods or run otherwise on Windows hosts. Let's have a quick look at AWS services that will be involved in building today's solution. Although AWS App Mesh is the star of today's show, we will need to employ a few other services and components to build a solution that represents a real-life use case to the decent level of fidelity. We will use Amazon Elastic Kubernetes Service, EKS, to run our ASP.NET Core applications as Linux containers, AWS Fargate to make our Kubernetes clusters serverless, meaning not exposing us to headaches of cluster node virtual machine management, Amazon Elastic Container Registry, ECR, which is a container image storage where we'll stage our application container images to make them available for the Kubernetes cluster. Amazon App Mesh itself, of course, the nicer, gentler, and less limiting kind of logical cluster. Application Load Balancer, ALB, for managing inbound traffic before it reaches the cluster, and AWS X-Ray to see application traffic traces and to see graphical visualization of service maps. We will also use integration components that are not services in their own right, but are necessary for building an end-to-end solution. App Mesh Controller and AWS Kubernetes integration, letting Kubernetes resources to be a part of an App Mesh. ALB Ingress Controller, making Amazon Application Load Balancer to be a known entity in the Kubernetes cluster. Ingress Gateway, an intermediary between the inbound traffic arriving from the load balancer and the rest of the mesh resources. Ingress Gateway is the first point where the inbound traffic becomes visible to and managed by the App Mesh. Okay, we are done with appetizers and about to start the main course, building things. What are we going to build today? Just look at this scary busy infrastructure diagram with lots of boxes and arrows. It is our target solution architecture for today. My promise to you is that if you stick with me, it will make sense at the end of the video. We're going to start small though, with this nearly empty page and add components one after another by deploying AWS services and Kubernetes resources step by step. Still, let me quickly go back and discuss our target solution again. In a nutshell, we will deploy our client-server application to the Kubernetes cluster and make front-end client app accessible from the internet while keeping the back-end service locked down and inaccessible from the outside. We will also showcase the canary rollout pattern, where a new version of an application is seamlessly added as a partial handler of inbound requests with gradual shifting of traffic from the old version of the application to the new. As far as infrastructure goes, at the high level, we will have an AWS account with several AWS services that live outside of either App Mesh or the Kubernetes cluster. Specifically, we will use Elastic Container Registry, ECR, Application Load Balancer, ALB, and AWS X-Ray that will render our service dependency maps and let us see service call traces. We'll have a single Kubernetes cluster running on Amazon Elastic Kubernetes Service, EKS, represented by a gray box with the icon having letter K in the top left corner. The app mesh that in our simplified solution will cover only one Kubernetes namespace. We will have two versions of the Color application running on Kubernetes as containers, and fronted by a virtual service named Color Canary, which also will have a virtual router to split the traffic between version 1 and 2 of the Color service. There will be a Color client application container, and finally an Ingress Gateway linked to Amazon Application Load Balancer that together let internet traffic in. Everything pink is part of the app mesh. And as we just discussed, any resource on the diagram having word virtual in its name does not really exist as a tangible entity, but rather is just a configuration item for an Envoy proxy. While we're here, in case you are not familiar with different types of App Mesh resources, let me introduce a few resource types that we will rely on today. Virtual nodes represent sets of running containers, which in Kubernetes translates to sets of pods, similar to how Kubernetes deployment represents a set of pods. Virtual services create an abstraction layer over virtual nodes and serve roughly the same purpose as Kubernetes services. Virtual routers are resources for routing and traffic shifting and are usually referenced by virtual services and gateway routes. Gateway routes are resources for routing external traffic from an ingress gateway to virtual services. The final note before we get our hands dirty and start building things is that for meshes using DNS mode of service address resolution, regular Kubernetes services need to be created for the purpose of domain name resolution, even though Kubernetes services are not really used for traffic handling when mesh is in charge. And now we start our walkthrough. I will be using command line tools with PowerShell, but I will occasionally switch to AWS Web Console to see results of our labor there as well. For time-consuming operations, I will edit out wait delays to skip forward the video, and I will let you know when I've done that. Okay, let's get started. First thing we create is an Amazon Elastic Kubernetes service cluster named App Mesh Demo. I will be using PowerShell variables, so it would be easier to reuse these commands with your own values if you choose to do so. This command will create Kubernetes clusters that will use Fargate server compute nodes, meaning virtual machine instances running our Kubernetes pods will not show up in the list of EC2 instances in AWS Web Console. The new cluster will have a standard predefined system namespace named kubesystem, where we will install some of the components, hence the namespace is here on the diagram. Provisioning the cluster will take a few minutes, so I am going to edit out the wait time to skip forward to the completion of the process. Let's take a look at the EKS cluster in AWS Console. It has a Fargate profile, telling EKS control plane to schedule all pods in the default and kubesystem Kubernetes namespaces to run on serverless Fargate. Now let's authorize kubectl command line tool to talk to the Kubernetes cluster we just created. We can now run kubectl CLI commands like kubectl get pods, or we can use VS Code and its Kubernetes extension to view and manage our Kubernetes cluster. There we can see Kubernetes namespaces, nodes, deployments and their pods, services. You get the idea. VS Code Kubernetes plugin might be an easy option for those accustomed to GUI operating systems. We will use both command line and VS Code pretty extensively today. Our sample project is on GitHub. Let's clone and run it. We'll create a directory for all our open source assets first. Next, we clone the sample application GitHub repository and simplify sample folder name. Now let's switch to the correct branch and open the solution in Visual Studio. There we have two projects, a service and a client. Each project has configuration settings defined in their respective appsettings.json files. Service application has a setting telling which color to return to the client, and the client application has address of the service in its configuration file. Now let me run both applications from Visual Studio. I'm starting with service application first. Its landing page shows us a REST service OpenAPI specification. And by changing URL in the browser by appending /color, I can get back the color defined in the service application's configuration settings. Next, I will start the client application. If we configure it correctly, when I click this Invoke Service link, we should see a message with the background color returned by the color service. Alright, both applications look good now. Now let me run both applications as Docker containers. I will build service application Docker image first. If this Docker build command looks a bit unusual to you, that's because Docker files generated by the Visual Studio have this quirk where Docker context should be one folder level above the location of the Docker file. Hence, we're specifying both the context and the Docker file location explicitly. And let's check that the image has built successfully. Let's run our color service container and make it accessible on port 6001. You may have noticed that I did override the color configuration setting via environment variable. I have configured the service to return magenta as a color when the color service is called, and make sure that our service is running in the container well. Good. Next step is to build client application container image. Let's run the client in such a way that will let the client find the service. The --link command line parameter will make color service hostname HTTP color-service resolvable on the client container, and the -e parameter configures client application settings so that the client will call the service at that HTTP address. And open containerized client application in the browser and see whether everything works as expected. Now that we've made sure our application can run in containers, let's upload their images to AWS to make images available to Kubernetes. We'll start this with creating two Elastic Container Registry repositories, one for service images and one for client images. Let's take a look at these repositories in AWS Web Console. And let's copy ECR URI so we could push application images to AWS repositories. Now let's authorize Docker to push images to our ECR repositories. And let us tag and push our application container images to AWS. The final step here is to ensure our images are up in the repository. At this point, we have tested the sample application and staged our application container images. By the way, if you decide to run through the flow yourself, you could do this container-related part of the build while Kubernetes cluster is getting provisioned instead of waiting for provisioning to complete. Okay, we are done with this part and can get to the task of building the mesh. Before creating the mesh, though, we need to install a couple of integration components in our Kubernetes cluster. One to support App Mesh and another to support AWS Application Load Balancer as a point of external traffic ingress. Kubernetes extensions and integration components are typically implemented as Kubernetes controllers. So we'll install App Mesh Controller and ALB Ingress Controller to get us to the point where our architecture will match this picture. Typically, steps of installing App Mesh and ALB Ingress Controller are kind of a chore, so to streamline the process, I have created a few fairly generic parameterized PowerShell scripts that will reduce the number of steps and make the process simpler. These scripts are available on GitHub, and you are welcome to use them if you so choose. Okay, here we go. I will prepare a directory for the script, clone the GitHub repository with scripts, and simplify the directory name. Our scripts are here. Let's install the App Mesh controller using App Mesh Controller EKS installer PowerShell script. Command above installs App Mesh with AWS X-Ray tracing integration and assigns App Mesh Controller Kubernetes namespace to serverless Fargate nodes. Let's run it. It will take a minute or two to complete, so I will fast forward the video. We can install ALB Ingress Controller in parallel in another PowerShell window. I will need to copy a couple of PowerShell variables first, and start installation by running ALB Ingress Controller installer script. Let it run. I will use the following command to wait for ALB Ingress Controller readiness. And in another window, similar command to wait for the App Mesh Controller readiness. I will edit out the wait so we could just cut to the completion of the installation of both integration components. Now, after we have installed necessary AWS Kubernetes integration components, next we will create and configure Kubernetes namespace for our sample applications. We will make the namespace eligible to join the App Mesh, which we will create shortly afterwards. And we will also ensure that Kubernetes container pods located in this namespace will run on serverless Fargate cluster nodes. Also, we will create a Kubernetes service account with sufficient AWS access rights for pods to receive Envoy proxy configuration data while running on serverless Fargate cluster nodes. But let's do one thing at a time. First, we create a Kubernetes namespace called color space. Now we will label the namespace with values telling App Mesh controller to treat our new Kubernetes namespace as a member of the App Mesh. First label is to tell the App Mesh controller to inject sidecar Envoy containers into pods running in this namespace. Next, we will assign this new Kubernetes namespace to Fargate nodes by creating EKS Fargate profile for the color space namespace. It will take a minute or two to complete, so I will skip ahead. And now we will tell the App Mesh controller which mesh the namespace will be a part of. We will name our mesh color mesh and label the namespace with the mesh name. Let's see our new namespace labels in VS Code. And the last sub-step here is to create Kubernetes service account that will grant Kubernetes pods running on Fargate correct access rights to receive Envoy configuration data. For that, we will use service account for Envoy on EKS Fargate PowerShell script, which we have cloned from the GitHub a few minutes ago. The script has created a variable storing the service account name. Since Visual Studio Code Kubernetes plugin lacks ability to show service accounts, we will use command line to verify that service account is indeed created. Okay, service account is there, and this means we are done with configuring our namespace and are ready to go to the next step. Now it's time to create the App Mesh itself. The name of the mesh is already set in a PowerShell variable. It's color mesh. To simplify the step of creating an AWS App Mesh, I have created a super simple Helm chart which takes mesh name as an installation parameter, so let's get the chart from the GitHub. Now let's have a dry run of our mesh installation to see Kubernetes manifest that will be applied if we run installation for real. This is a Kubernetes manifest that will create the App Mesh in both AWS and as a custom Kubernetes resource. Let's apply the manifest and see the App Mesh created on AWS. We are now only one step short of installing our applications. Creating an App Mesh Ingress gateway, together with ALB-based Kubernetes Ingress resource, is going to be our last one-time infrastructure component installation step. After this step, our Kubernetes cluster and all other required infrastructure components are going to be fully configured. Ingress Gateway is an App Mesh resource that receives requests from outside of the App Mesh and routes them to App Mesh virtual services using gateway route resources. Ingress Gateway, being essentially a standalone Envoy pod, ensures that request traceability starts as soon as the request enters the mesh. Ingress Gateway supports different ways of ingesting traffic from the outside. We have prepared for that at our previous step by installing ALB Ingress Controller. Under the hood, Ingress Gateway is a standalone Envoy proxy, and to install it on Kubernetes, we'll run the Helm chart I created, which simplifies this step. The chart is in the same GitHub repository, which we have used a minute ago to create App Mesh itself. Okay, let's do it. We'll need to come up with a unique name for the Ingress Gateway. For example, we could do it with the PowerShell like so. That will be our Ingress Gateway name. Every Kubernetes namespace that is a part of an App Mesh should have one Ingress Gateway. Now we are ready for the dry run of the installation of the Ingress Gateway. Command above specifies following Helm chart installation parameters: a Kubernetes namespace, an installation release name, a Helm chart folder location, an AWS region, the appmesh.fargate pod service account, which specifies Kubernetes service account for running Envoy proxies on Fargate. Ingress.enabled equals true lets external traffic enter the Kubernetes cluster. And ingress.alb equals true says that we'll be using ALB for our ingress and not NLB. Let's run the command. As you can see, we will have multiple Kubernetes resources created for the Ingress Gateway. Specifics are outside the scope of this video, but feel free to explore these manifests on your own. Let's run the installation for real now. Alright, but we also need to bind our new Ingress Gateway to the Kubernetes namespace by labeling the namespace with the name of the gateway. Now we can set up wait for the Ingress Gateway readiness like so. Alright, we are done installing Ingress Gateway. That was the first component we have added to the mesh. Let's take a look at the App Mesh resource in AWS Web Console. We see the virtual gateway resource there, and we can see its Kubernetes counterpart in the VS Code among Kubernetes custom resources. Let's quickly recap results of this step. Kubernetes namespace, where we will install our applications, now has a label with the name of the Ingress Gateway. There it is. We also have Ingress Gateway Kubernetes pod up and running. Please note the name of the gateway pod. We will need it in a moment. And we have the AWS Application Load Balancer, ALB, which we can see in AWS console. Here's the listeners. And here's the targets. As you can see, the load balancer is forwarding traffic to the Ingress Gateway pod. I will also copy the DNS name of the load balancer and paste it in the browser. I hit enter and I get bad gateway response, which is expected because Ingress Gateway has nothing downstream from it. Okay, we have prepared our target infrastructure. Now it's time to create Kubernetes installation packages, Helm charts, for each of our two sample applications. Color service will be first. We will make service return color green, and that will be version 1 of the service. Also, for demo purposes, I will temporarily expose the service on the internet so we could test our entire infrastructure by ensuring we can flow a request starting from the internet to the service inside the mesh and see request trace data in AWS X-Ray Service Map. And after we are done with the test, I will remove the gateway route, which is a virtual resource exposing the service on the internet to lock down our service inside the mesh. An important thing to note is that once a Kubernetes namespace is made to be a part of an app mesh, we can't use regular Kubernetes deployment to run a pod in that namespace, without that pod also having a corresponding virtual node. I need to stress this again. We can't use regular Kubernetes manifests to install application in a mesh namespace. Only mesh-aware installations can do that. This means App Mesh is not really a drop-in type of component. Once you decided to use App Mesh, that's a commitment to build your Helm charts that will include creation of App Mesh resources. That's why the Helm charts I have created for this video let you deploy your application to both regular EKS cluster namespaces as well as to namespaces that are a part of an App Mesh. To switch the Helm chart between regular EKS and App Mesh enabled installations, all you need to do is to change a few installation parameters in the values.yaml file of the Helm chart. In this demo, I am focusing solely on installation parameters targeting App Mesh. We start with cloning GitHub repository containing general-purpose Helm charts that require very minimal changes in order to accommodate typical web applications when they're installed on Kubernetes, whether the target is a regular EKS cluster or an App Mesh. Then we will tweak these Helm Chart installation parameters for each of our two sample projects, the service and the client. First thing first though, let's clone the GitHub repository with App Mesh-aware general-purpose application installation Helm charts. I will rename the folder with charts and name it Helm, and remove Git repo data from the folder. Now let's copy our generic Helm chart installation templates to both service and client Visual Studio projects. Templates making up the chart don't need to be changed, so I will not stop to explain what's inside. All the changes that we need to make will be limited to installation parameters. Therefore, I would like to show you only chart.yaml and values.yaml files, where default installation parameter values are set. We will change a few of these parameter values and we'll be on our way. If you have ever created an installer for a Windows application using Install Shield or a similar tool, the flow basically consists of packaging your application binaries and setting default installation parameters like destination installation path and so on. With Helm Chart, similar logic applies. You tell the location of your installation binaries, namely the location of the container image, and then you also set parameter values for the installer. Let's do that. It will only take a minute. Let's set the name and the description of the application as you might have for an MSI installer in Install Shield. Most of installation parameters are in the values.yaml file though. The most important parameter of the installation is the location of the container image. We'll retrieve it using command line. And paste it in the values.yaml. Now we'll tell the chart we'll be installing the app in an App Mesh. Next, we supply the Kubernetes service account name for Fargate pods having Envoy proxy. And for the caller service application, we need to change the default health check path because default path of the caller service, the /, does redirection, and that 302 HTTP response status is treated as a non-success by the system. Hence, we set the health check path so it would return to 100 when all is good. That's all the default values we needed to change for the service application Helm chart, believe it or not. We'll also change some installation values from the command line when we will be installing the service, but that approach is for parameters changing with each installation. Okay, we are ready to validate our installation. Command line above will generate Kubernetes manifest that will be applied in real installation. Helm install command install the package located in the chart subdirectory and creates installation release named caller service v1. Also, the installation command overrides a couple of default installation parameters. We set application container environment variable that will override color configuration value from application's appsettings.json to return color green. And another installation parameter will expose our caller service to the internet. We do that only temporarily to test our environment and ensure we have set everything up correctly. Let's run the command. We can see Kubernetes resources that will be created when we run installation for real. We get customary Kubernetes deployment and service resources, but we also get App Mesh resources like virtual node, virtual service, and a gateway route. Let's install the application for real by rerunning the previous command without the dry run flag. Great. Next command will list packages installed in a current namespace on current Kubernetes cluster. We can see all packages we have installed so far in the current namespace using Helm. App Mesh package, Ingress Gateway package, and Caller Service v1 package we have just installed. To be precise, this list contains named releases rather than packages, because unlike MSI, the Windows installer, any Helm package can be easily installed more than once in the same Kubernetes namespace as long as each installation gets a unique release name and the chart is designed to generate unique Kubernetes resource names. Our chart does generate unique resource names based on the release name, so this will let us install another version of Caller Service application later without changing any properties of the installation package. Now let's wait for service application pod readiness. Alright, everything is ready, and the ultimate test for our deployed application is to browse to our service and see what happens. And we've got green as a response. That is great. All our infrastructure installations and application installation have worked together successfully to deploy our first application to the App Mesh. But functionally, it is not different from regular application container deployment to EKS. What is different here is that if we go to the AWS X-ray page in the AWS console, we should see graphical representation of our service map. Let me send a few more requests through and then go to the X-ray page. On the X-ray service map, we can see the traffic pattern going from the client to the ingress gateway to the service. We can also see trace information if we click on service map elements and see performance and success error data about requests flying through the mesh. This is one of the most valuable features of AWS App Mesh in action. Easy integration with AWS X-ray and supplying rich traffic metadata to enable X-ray service map functionality. Let's also examine App Mesh resources we have created for our application as they are presented in AWS console. Our application virtual node, a virtual service, and a temporary gateway route that we're about to remove to lock our backend service down inside the App Mesh. Now that we have tested the environment end-to-end, I will remove the gateway route, and that will make the service inaccessible from outside the mesh. A bit later, we will install the front-end client web application and will make it accessible from outside the cluster. Okay, let's go back to the browser and make sure that the service is no longer accessible on the web. Okay, we are done with the version 1 of the Color service and with verifying that all other components we have installed so far are working as expected. Next, we will start using another important feature of AWS App Mesh, Virtual Router, which enables blue-green and canary rollouts and rollbacks of new application versions. At this step, we will put the canary-enabled endpoint in front of our Color service. The key to creating a canary-enabled endpoint in an App Mesh is identical to creating a regular Kubernetes canary endpoint. We need to tell the system about what label or labels define the set of Kubernetes pods that the canary endpoint will be fronting. Let's see which labels our Color Service v1 has. Color Service pods have multiple labels, but there are two relevant to our current task. App label with the value of Color Service, and the release label with the value of Color Service v1. As you can see, the app label is version agnostic and the release label is version dependent. Canary needs to send requests to any version of the application it serves, so in order to define our canary correctly, we will need to keep in mind that it needs to send requests to any Kubernetes pod that has app label value set to Color Service. Canary endpoint's lifecycle is quite different from the lifecycles of application resources. Because of this difference in life cycles and scopes, our application projects have second Helm chart, the canary chart, in addition to the chart we used at the previous step for installing the application itself. Canary chart creates a virtual service that serves as a version-agnostic network endpoint and a virtual router responsible for sending traffic to different versions of the application. We'll modify slightly our general-purpose canary Helm chart that is already part of our application project. Let's open Visual Studio and modify the chart.yaml file of the canary Helm chart. Here, as before, we set application name and application description. We save the file. Now we'll edit the values.yaml file. Here we specify the label that every Color Service pod will have, regardless of application version. And we also specify that the canary is to be created by using App Mesh virtual resources rather than with a regular Kubernetes service. That's all the changes we needed to make in canary values.yaml file, so we save the file and we are ready to install the Color Canary virtual service. Let's do the dry run of our canary installation first. Let's review this command. It tells Helm to install the content of the folder named chart and to name installation release as color-canary. We also do set a few installation parameters from the command line. We temporarily expose the Color Canary endpoint on the internet for testing purposes. And the last two lines of the command tell Canary to send traffic only to the caller service v1 virtual node. Let's run the command to see resources that will be created when we run the installation for real. We can see a gateway route that will make caller Canary temporarily accessible on the web for testing, a virtual service by which clients will call the caller service application, and a virtual router that is responsible for sending traffic down to specific application pods. Everything is looking good, so let's run the installation for real. Since the resources we create here are virtual and the only actual outcome here will be updating Envoy proxy configuration of the Ingress gateway, we should be able to go to the browser and reach our Canary endpoint right away at the /caller-canary path. Let me run a few requests through to make sure everything is working. Okay, our testing looks good, so I can drop the gateway route for the caller Canary as it is a backend service that does not need to be accessible on the web. To do that, I'm removing the outside traffic allowed parameter, which will revert to the default value set in the values.yaml file of the Canary Helm chart. Let us run it and make sure the caller Canary is no longer accessible on the web. Alright, everything is working as expected. It's worth noting that the net result of this step and the previous one, where we didn't have a canary and routed requests from the Ingress gateway directly to the caller service v1, is the same. Both configurations resulted in Envoy proxy running at the Ingress gateway, getting configuration settings that told it to direct requests to the caller service v1 pods. The benefit of the virtual Canary service is that we have an easy way of modifying it by installing the Canary Helm chart with different parameter values. Next step is deploying client application and ensuring it can call the caller service at the Canary endpoint and that the client is accessible on the web. As with the caller service application, we have already added the same general-purpose Helm chart to our client application project. Now we just need to edit the chart a little bit before we start using it. We'll start with editing chart.yaml file of the application chart in Visual Studio. We change the chart name, which serves as an application name. And we'll also provide relevant application description. No other changes are needed in the chart.yaml file, we can save it now. Next step is editing values.yaml file, the place for installer's default parameter values. Again, the first thing to specify is the location of the application container image. This command will copy client application image location URI to the clipboard. We can paste it as a value of the repository parameter. Next, we set the value of the caller service address pointing to the caller Canary virtual service. And edit the values of the App Mesh section. Enabled set to true to generate App Mesh based installation instead of pure Kubernetes installation. Again, we need to set the Fargate pod service account value to let client applications Envoy proxy run on Fargate. We can get the value from the Fargate pod account name PowerShell variable. Just a reminder, Fargate pod service account parameter should point to the Kubernetes service account mapped to an IAM role that has permissions to let Envoy proxy get its configuration settings. We have already used it twice, once for the Ingress gateway and once for the caller service. Outside traffic allowed set to true, we do it to let outside traffic to flow to the client application. Gateway route match prefix / will ensure that requests to the root path of the application load balancer will be sent to the caller client application. We can now do the dry run of the client application installation. Let's use Visual Studio to copy the path of the application folder and cd there. And run the command that should be pretty familiar to you by now. As with the caller service application, we see Kubernetes deployment and a service, as well as App Mesh resources, a virtual node, a virtual service, and a gateway route. Everything looks good, so let's run the installation for real. Let's set up the wait for application pod readiness. I will skip forward the video here. Okay, everything, the client, the service, and the Canary-enabled endpoint are in place, so if I test the client in a browser, everything should work. Great, we're getting green color returned by the service and it is shown by the client. It meant our Canary is sending 100% of the traffic to the caller service v1, which is our current production version of the caller service application. Now let's take a look at the AWS X-Ray service map. Notice we now have multiple traffic segments here, including hops between the ingress gateway and the client application, and then between the client and the color service v1. Also, let's see what we got in the AWS App Mesh page of the console. We got virtual gateway, which is the ingress gateway we have created a few steps ago, which points to the color client virtual service, which in turn has a virtual node. The virtual node points to the color canary backend service, which has a virtual router, currently pointing to the color service v1 virtual node. At this point, we are done with the prototype of the end-to-end solution that has only version 1 of the color service. Next, we'll see how rolling out version 2 of the color service will look like. In our example, color service v2 will play a role of the new version of the application, which after a bake-in period should replace previous production version. We need to change our current directory to point to the application folder of the color service application Helm Chart. And now we can install another release of the color service. This command will install color service application again, this time as the color service v2 release, and will set application color configuration setting value to blue. In the real world, instead of just changing application configuration setting, you will modify application source code, build and push new container image, and specify new image location as an installation parameter, either by modifying values.yaml file or using Helm install command line parameter. Let's run the command. And now let's use another way of reviewing Kubernetes manifest creating as part of the installation. We can see Kubernetes resources, a deployment, and a service, as well as App Mesh resources, a virtual node, and a virtual service. There is no gateway route this time because instead of connecting ingress gateway to the application pods directly, we will make color service v2 a part of the canary traffic split. Let's go back to the canary Helm Chart directory and upgrade our color canary installation by creating 2 virtual routes instead of just one we have right now. One route will stay pointing to the color service v1, and another new route will be sending traffic to the color service v2. We will also treat color service v1 as a stable but old production version of the application by directing 80% of the traffic to it, and color service v2 will be treated as an unproven new version. This configuration should result in our client showing green color approximately 4 times more frequently than blue color. Here's the command that will update the color canary to the configuration we want. The command will update existing color canary application installation by supplying parameters creating 2 virtual routes with 2080 traffic split expressed as target weight parameter values 1 and 4. Let's run the command. OK. And let's check whether all pods of the service color 2 are already up and running. Looks like everything is in place, so let's go to the color client browser page and run a few requests through. I am clicking and getting both blue and green, with color green popping up more frequently than the blue, which means our canary is in place and performing as expected. You have probably guessed that by repeatedly running Helm upgrade command with different values of target weights, we can keep shifting traffic incrementally or roll back 100% of the traffic to the old version in seconds if the new version turns out to be problematic. One could write a script that could watch service error rate and other performance metrics of both new and old versions, and if version 2 remains stable after each incremental traffic shift, automatically finish shifting 100% of traffic to the new version 2. OK, let's take another look at the AWS X-Ray service map now. Here it is. We see color client application calling both color service v1 and color service v2, and the number of calls is roughly 1 to 4. If we click on service map elements, we can see trace data related to that map element. Finally, let's see our App Mesh page in the AWS console and see how color canary virtual router is configured. As you see, it has 2 routes now, pointing to 2 different virtual nodes representing old and new versions of the color service. The final step of our solution build-out is to fully switch traffic to Color Service v2 without causing any disruption to clients. We'll do that in 2 steps. First, we will use Color Service Canary endpoint installer to shift 100% of Color Service traffic to Color Service v2. And if everything keeps working well, we'll uninstall Color Service v1 release. To shift the traffic from the Color Service v2, we'll run this command. This command updates Color Canary virtual router settings to send all traffic to Color Service v2. Let's run the command and test our client. As you can see, we started getting only blue color in just a matter of seconds. At this point, we could still switch everything back to version 1 if something went wrong with version 2. But we have tested version 2 and are confident it is stable, so we can now go ahead and uninstall Color Service v1. Let's go to VS Code to make sure Color Service v1 is gone. Alright, Color Service v1 is no longer there, meaning we have completed the process of replacing version 1 of the service application with version 2 without disrupting the client at all. Let's take one final look at the AWS App Mesh page, where we can no longer see Color Service v1, no virtual service, and no Color Service v1 route at the Canary virtual router. And let's also check out AWS X-Ray service map. We see now that all recent traffic went to the Color Service v2. So here we are. We have 2 ASP.NET Core applications absolutely unaware of AWS, Kubernetes, or any other infrastructure or compute service outside of just being compatible with Docker. We used open source tools to simplify provisioning of Amazon EKS cluster, AWS App Mesh, and to install required integration components. And then we used general purpose Helm charts compatible with both regular Kubernetes and with AWS App Mesh to install client and service applications and to create a canary-enabled router endpoint for the service application. Finally, we were able to use AWS X-Ray to see application trace data and the service map. And that is how AWS App Mesh enables network controls and consistent visibility for your container workloads. If you have used your own AWS account to build solution described in this video, following commands will let you remove most of AWS resources created here. You may treat this video as a lab walkthrough. All parts necessary to build this solution are accessible on the web, so you could practice building this solution yourself. On top of that, you could improve it by adding canary-enabled endpoint to the client application. We have not done that in this video, but all ingredients are in place. Please write the comment if you completed this challenge. We would like to know if you succeeded. To help with implementing this little homework task, here is a brief overview of the steps you may take to solve the problem. Well, this is it. Thank you very much for watching this video. Please post a comment and rate it to let us know whether this video was useful. Thanks again, and please be sure to explore other AWS videos.